Ever wondered how the concept of infinity, a notion so vast and elusive, came to be understood in the world of mathematics? This enigma has fascinated thinkers since the dawn of civilization. Ancient cultures grappled with the idea of the infinite, striving to encapsulate its enormity within their rudimentary mathematical frameworks. Yet, without the formal structures we're familiar with today, they could only scratch the surface of this profound concept. In the ancient world, the infinite was often viewed as a philosophical, rather than a mathematical concept. The ancient Greeks, for instance, contemplated the infinite in the philosophical works of Zeno and his paradoxes. Zeno's paradoxes are a series of thought experiments that play with the concept of infinity, showcasing its inherent contradictions and complexities. However, the Greeks, like many other civilizations, lacked the mathematical language to fully articulate the infinite. They saw it as an abstract idea, a concept beyond the grasp of numbers and calculations. The Greek mathematician Euclid even went as far as to declare that the infinite does not exist in the same way as finite numbers do, illustrating the struggle early mathematicians had in wrestling with the concept. Fast forward to the Middle Ages, and we find mathematicians still wrestling with the concept of infinity. In this era, infinity was often associated with the divine, a concept so vast and incomprehensible that it could only be attributed to a higher power. This interpretation, while spiritually rich, didn't advance the mathematical understanding of the infinite. It wasn't until the advent of more sophisticated mathematical theories and tools that the concept of infinity began to emerge from the realm of philosophy and theology, and find a home within the world of mathematics. The landscape of this vast concept started to change, and the infinite became less of a metaphysical enigma and more of a mathematical tool. It wasn't until the late 19th century that the concept of infinity began to take on a more concrete form in the mathematical world. This was the dawn of a new era, an era marked by bold exploration and groundbreaking discoveries. The infinite was no longer an enigma, but a frontier, waiting to be explored and understood. Enter Georg Cantor, a mathematician whose groundbreaking work changed the way we perceive infinity. Cantor, in the late 19th century, dared to tread where many feared to step, the realm of mathematical infinity. His audacious explorations led him to develop the revolutionary theory of sets, a theory that fundamentally altered our understanding of the infinite. Cantor's set theory was a brilliant departure from traditional arithmetic. He boldly proposed that infinity is not a singular monolithic entity, but rather comes in different sizes, or as he termed it, cardinalities. This was a radical idea, challenging centuries of mathematical thought. Infinity was no longer intangible and elusive, but something that could be classified, ordered, and understood. In this new perspective, the infinite was not just a concept, but an entity with structure and properties. Cantor introduced us to the world of infinite sets, collections of elements that are not limited in number. He showed us that there are as many even numbers as there are numbers in total, a concept that might seem counterintuitive but is a fundamental truth in the realm of the infinite. Moreover, Cantor's work unveiled the concept of ordinality, which delved into the order type of sets, providing a new lens to view infinite collections. He explored the continuum hypothesis, a proposition dealing with the sizes of infinite sets, revealing the richly woven tapestry of infinite possibilities. However, Cantor's revolutionary ideas were not readily accepted. His work sparked controversy, with some of his contemporaries finding it too radical, too removed from established mathematical norms. But Cantor persevered, his conviction unshaken, his vision undeterred. His profound insights opened new avenues for mathematical exploration, giving us the tools to navigate the vast expanse of mathematical infinity. His work laid the groundwork for a nuanced understanding of the infinite, a foundation upon which modern mathematics has been built. Cantor's work set the stage for a refined understanding of the infinite, but the journey was far from over. This was just the beginning of a fascinating journey, a journey that continues to this day, pushing the boundaries of our understanding of the infinite. The 17th century saw another pivotal moment in the story of infinity with the advent of calculus. This revolutionary branch of mathematics, introduced by giants of the mathematical world, Isaac Newton and Gottfried Leibniz, transformed the way we comprehend changing quantities. Picture this. You're trying to calculate the speed of a car at a particular moment. Before calculus, this was a daunting task. But Newton and Leibniz introduced the concepts of derivatives and integrals, tools that made it possible to capture the essence of change and motion. They provided a way to break down infinite processes into small, manageable pieces, then sum them all up, a concept known as infinitesimal calculus. This was a monumental step forward. Suddenly, mathematicians could measure curves with precision, calculate areas under complex shapes, and solve problems involving motion and change. The infinite was no longer a philosophical concept, but a mathematical tool, tractable and usable. But the story doesn't end there. The initial formulations of calculus were intuitive and powerful, yet they lacked a rigorous foundation. This raised questions and sparked debates, leading to what we now call the foundational crisis in mathematics. The infinite processes calculus dealt with were tricky, and the notion of infinitesimals, numbers closer to zero than any real number but not zero, was puzzling. The 19th century saw a solution to this crisis with the subsequent development of mathematical analysis. This discipline, which includes calculus, real analysis, and complex analysis, solidified the foundations of calculus. It provided a robust framework for dealing with infinite processes and sequences, assuring mathematicians that their calculations were sound and reliable. This development of mathematical analysis was like constructing a sturdy bridge over the swirling, chaotic sea of infinite processes. It allowed mathematicians to traverse the infinite with confidence, knowing that their footing was secure. The development of calculus added another dimension to the mathematical understanding of infinity, yet it also brought to light new challenges. But as we'll see, these challenges only served to push the boundaries of mathematics even further. The path to understanding infinity has been fraught with intellectual challenges and paradoxes. One of the most intriguing paradoxes that emerged from the exploration of mathematical infinity is Russell's paradox. Named after the British philosopher and logician Bertrand Russell, this paradox arose from the set theory, and it threw a wrench into the previously accepted notions of mathematical logic. In simple terms, Russell's paradox questions whether a set of all sets that do not contain themselves contains itself. If it does, then by definition it shouldn't. But if it doesn't, then by definition it should. This circular reasoning is a classic example of a catch-22 situation, a paradox that sent shockwaves through the mathematical community. Beyond Russell's paradox, other antinomies or self-contradictions have also emerged, pushing mathematicians to reevaluate their understanding of infinity and the logical foundations of their discipline. These paradoxes have highlighted the delicate balance between the seemingly boundless opportunities offered by mathematical exploration and the need for a coherent and consistent mathematical framework. For instance, consider the paradox of the Grand Hotel, a thought experiment that illustrates the bizarre nature of infinity. Imagine a hotel with an infinite number of rooms, all occupied. Despite being full, the hotel can still accommodate new guests, simply by shifting each current guest to the next room. This paradox challenges our intuition about quantities and space, highlighting the complexities involved in grappling with the concept of infinity. Yet, it's within these paradoxes and challenges that the true beauty of mathematics shines. These are not roadblocks, but rather stepping stones, pushing the boundaries of our understanding and paving the way for new discoveries. They represent the ever-evolving nature of mathematics, a discipline that continually refines and expands its own foundations. Through these challenges, the quest to understand infinity has become a dynamic journey, marked by intellectual curiosity and unrelenting determination. And it's this journey that has led to profound insights into the nature of reality, from the cosmos's vast expanses to the infinitesimal fabric of quantum mechanics. These challenges, while daunting, have only fueled the determination of mathematicians to conquer the infinite. The conquest of mathematical infinity has far-reaching implications beyond the realm of mathematics. This statement rings particularly true when we consider the intricate relationship between mathematics and physics. The concept of infinity, once reserved for the musings of philosophers and mathematicians, now finds itself at the heart of our understanding of the universe. Let's consider the cosmos, a vast expanse that appears to stretch into infinity. The mathematical concept of infinity becomes indispensable when we attempt to describe the universe's size, the number of galaxies it contains, or even the potential for multiple universes. In this sense, infinity allows us to articulate the seemingly inexpressible, giving us a language to describe the boundless celestial expanses. On the other hand, the infinitesimally small world of quantum mechanics also leans heavily on the concept of infinity. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, often deals with quantities that approach the infinite. This might seem counterintuitive, but it's in these tiny realms that infinity plays a critical role, helping physicists make sense of the strange and often paradoxical behavior of quantum particles. The unity between mathematics and the physical sciences is a testament to the power of mathematical infinity. It's this unity that has allowed us to make profound discoveries about the fundamental fabric of our universe. From the discovery of gravitational waves to the exploration of quantum fields, the concept of infinity has been instrumental, underpinning our most groundbreaking scientific achievements. But this isn't where the story ends. The journey into the infinite continues, with new theories and ideas pushing the boundaries of our understanding every day. As we delve deeper into the mathematical infinity, we're not just unlocking the secrets of numbers, we're gaining a deeper understanding of the universe itself, its origin, its structure, and perhaps even its destiny. As we continue to explore the vast expanse of mathematical infinity, we not only uncover the secrets of numbers, but gain deeper insights into the very essence of our universe.